Hello everyone, and welcome to our first lecture this semester. We begin with chapter 17 in the textbook. The title of the chapter is Electric Charge and Electric Field. Basically, there are two major topics in this chapter. The first one is called Coulomb's Law, and the second one is the concept of the electric field. So those are the two topics that I'm going to be covering during this lecture, and I will be covering in, I'll give you a brief outline of what the subject is all about, and I'm going to spend the rest of the lecture, or the video lecture rather, working out problems, examples from the chapter, and some of the homework problems, at least two. I am thinking of those two difficult ones, and I'm going to do them for you. Before I begin, I would like to ask you to please, before you watch any video lecture in the future, please do your reading assignment. Make sure that you read the chapter first before you come in and watch the video lecture. The reason for that is because I don't cover everything. It would honestly take me hours to cover everything in video time. So I will be just covering the basic topics under the assumption that you have already done your reading assignment and you have a good idea what the topic is all about, okay? So my job here really is to teach you how to solve problems that are related to the topic that we are studying. So anyway, we begin the chapter with the concept of Coulomb's law. But before I mention that, here is the chapter title here. I forgot to mention last time, if you need to look up a unit conversion, sometimes you need that. You can go there to the unit conversion factor. This is an Appendix D if you want to do that. You will find it right there. I just thought to mention it because in the book it is right on the first page of the hard copy, but in the ebook it is in the appendix. That's all. I just wanted to mention that. All right, let's begin our go back to the chapter. It's page Coulomb's law, page 532. It should take me there very quickly. There it is. This is the law right here, but I know I'll come back to the book in a second. I want to use my OneNote right there. So we begin with Coulomb's law. Coulomb's law of electrostatics, and it basically says the following. Before I talk about it, if you remember from previous class in your physics 151, you have studied Newton's law of gravitation, and it basically says if you have two masses, say one mass here, mass 1, and then I have another mass here, mass 2, and let's say that they are separated by a distance r, there will be a gravitational pull between them, such as, say, the moon and the earth, or the earth and the sun, and so on. So there will be a force of attraction between them, F, and this force is equal to the product of the two masses, m1 times m2, divided by their distance squared, up to a constant, g. We refer to it as the universal gravitational constant, right? And we call that the gravitational law, or the inverse square law. We call it the inverse square law because here the force is indirectly proportional to 1 over r squared. You see what I'm saying? So it's called the inverse square law. We have similar situation when it comes to electrostatics. When we talk about electrostatic, we're talking about charges. And charges, they come in two flavors, of course. You get a positive charge and a negative charge. And of course, if you remember from your middle school science course, opposite charges attract each other, and like charges such as positive repel each other, correct? And negative charges as well, they repel each other. We don't have something like this for gravitation. I mean, we don't have say positive mass and negative mass. We just have masses and force. The gravitational force is always attractive. But for electrostatics, the study of, so it depends on the charge, if it's positive or negative. So positive, opposite attract, and like charges repel each other. So we have a force. So let me draw a diagram first. So let's say, for example, I have two charges, one positive and one negative, and they are separated by a distance r. And by the way, the symbol for the charge is Q, and I write it as Q like that. Okay, it's kind of a funny looking Q, but that's how I write it. I'm going to call that Q1 and Q2, and they are separated by a distance r. Remember, the r here is the distance between the two centers. Okay, so in this case, there will be a force, electrostatic force or Coulombic force between them. This force is basically similar to the gravitational force that we just talked about. It is the product of the two charges, Q1 times Q2, divided by their distance squared. As you can see, this is also an inverse square law, up to a constant k, small letter k. Okay, so this g here, we call it the universal gravitational constant. This k, we call it the electrostatic constant. Okay, and this value, it has a certain value to it. It is approximately 9 times 10 to the 9. The unit on it is Newton meter squared over Coulomb squared. Coulomb, of course, is the unit of the charge. I assume you've done your reading assignment and you know all about that. Another way of writing it is by saying, in a symbolic way, K is also equal to 1 over 4 pi epsilon naught, where epsilon naught here is a constant. It's called the permittivity of free space, and it is equal to 8.85 times 10 to the negative 12, and whatever unit it is. What's the unit on that? It is Coulomb squared over, I could never memorize it, over Newton per meter squared. Okay, this is called the permittivity of free space. Just a constant. You don't need to worry about it, but just basically take it as a constant. We'll talk more about it later when we cover electromagnetic waves, but this is also a constant. Okay, so that's basically what Coulomb's law is. So I'm going to spend some time showing you how to apply this law. But before I do that, I want to talk a little bit about charges in general. So we said that the symbol of the charge is Q. Sometimes we write it as big Q, and the unit of it is the Coulomb. It's a capital C. When I put in bracket, it means the unit of. So this is the capital C is a Coulomb, and Coulomb as a unit by its own nature is a very, very large unit. Okay, I mean, it's like think of it like I'm trying to measure your height in miles. I mean, I could do it, but it's just the mile is too large of a unit for your height. It would be more fitting to use feet or inches for your height, or centimeters and meters. But mile is just too big. And that's the same thing for the Coulomb. The Coulomb is a very, very large unit when it comes to charges. So most of the time when you're reading a problem, you don't really see Coulomb. You say, for example, it will say something like a charge of, say, 5 nanocoulomb or microcoulomb. Okay, could be picocoulomb. Nano here means 10 to the negative 9 coulomb. That's a nano. The micro 10 to the negative 6 coulomb, a millionth. Okay, a nano is a billionth, a micro is a millionth, and a picocoulomb 10 to the negative 12 coulomb, which is a trillionth. You see what I'm saying? They are good to remember. So we say that most of the time, those are the kind of unit that you will see for the Coulomb, either nano or micro. Those are the more popular ones. You see what I'm saying? Okay. That's one thing. The second thing is we have something called the fundamental charge. The fundamental charge, it's basically the smallest unit of charge. Okay, that's one way to think about it. The smallest unit of charge. In other words, any charge of anything, you know, say something of a charge Q equal 15 nanocoulomb, something like that. Okay, this charge is really a number of fundamental charges. Okay, so this is basically one way to think about it. It's like the building block of any charge Q. In other words, the fundamental charge, which has a symbol E, small letter E, is equal to, it's a number, 1.602 times 10 to the negative 19 Coulomb. It's a really tiny number, as you can see. It's much, much smaller than the trillionth, the picocoulomb, or the micro, or the nano. It's much, much smaller. As you can see, it is 10 to the negative 19. Okay, very, very tiny. And like I said, any charge that you would read, say, for example, a charge of an ionized atom, or an ion, or a cation, whatever it is, any charge is a combination of a number of fundamental charges. You got it? An example, the electron, okay? The charge on the electron is basically the fundamental charge, okay? So the charge of the electron is 1e, okay? And that e is this number, 1.602 times 10 to the negative 19. Also, and of course it's a negative, so the charge on the electron is a negative e, which makes it negative 1.602 times 10 to the negative 19 Coulomb. For the proton, it's also excuse me, is equal. The charge on the proton is also fundamental charge E, but it is positive. So it's the same number, except it's a positive number. Okay. So let's assume hypothetically, let's say, I'll give you an example here. Let's say, for example, I have an ion, okay? And let's say this ion has a charge of Q equals to, let's say, 1 nanocoulomb, okay? So what does that mean? It means this 1 nanocoulomb is made out of a number of electrons. Okay, not protons, always a number of electrons. It's made out of a number of electrons, and this number of electrons add up to 1 nano. Got it? Let me repeat it again. If I have a charge, any charge, say an ion, and it is the Q of that ion is 1 nanocoulomb, okay? This means that this ion is made out of electrons. Maybe I should put a minus sign. I'm not sure. It's an ion, a negative or positive. I think it's a positive, negative. I think it's a negative, isn't it? I mean, it doesn't matter for our argument, but let's assume it's negative. Hold on, let me look it up. Sorry about that. Ion is negative or positive? I think it's positive. We're just going to assume it's positive, but I could be wrong. So let's say I have an ion, repeat what I said. So I have 1 nanocoulomb. I want to know how many electrons make up this 1 nano. Well, how do I do that? Well, here's one formula we can think of, that Q is equal to the number of electrons, I'm going to call it N sub E, times the fundamental charge. Make sense? So in this case, N sub E, which is the number of electrons, is equal to Q over the fundamental charge. So I have here 1 nanocoulomb over the fundamental charge is 1.602 times 10 to the negative 19. As you can see, I'm ignoring the minus sign. They're not important. I'm more interested in the number of electrons. Are they 5, 6 or something like that? Number of them. So in this case, I'm going to be 10 to the negative 19 Coulomb over 1.602 times 10 to the negative 19 Coulomb. Then I would use my calculator. I hope you brought your calculator with you and a notebook to take notes. So I'm going to use my calculator here. Oops, the nano here, I apologize. The nano is a negative 9, right? So that's going to be 1 negative 9 divided by 1.602 negative 19. Answer. So I'm going to have a very, very large number, and I'm going to convert it to scientific notation. So the number of electrons in this case is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to be equal to 6.24 times 10 to the 9 electrons. So in other words, if I take this many electrons, okay, these are electrons, which is 6.24 billion electrons. If I take this many electrons, okay, and put them all together, and if I would measure the total charge of those electrons, it's going to be basically 1 nanocoulomb. You got it? Okay. There is an example related to that in the book. It's example 17.1. Let me go over it very quickly. Talks about this stuff here. Oh, let me take the book. Show you the book. The book is here. Yeah. I need to go to page 534. There we go. As you can see, you can move from page to page with by just putting the page number right here. Anyway, here is the example right there. It says, in this example, we will use the quantization of charge to determine the number of excess electrons in an object. So A. So we have A, B, two parts. A large plastic block has a net charge of -1 microcoulomb. Okay? So we have a charge of -1 microcoulomb. He's asking how many more electrons than protons are in the block. Basically, he wants to know how many electrons make up 1 microcoulomb. You see what I'm saying? So we're going to do the same thing that I just showed you for that. Maybe I could move it on the side like this. So what I'm going to do, that's for part A. So I have here the charge is equal to number of electrons times the fundamental charge, right? And so therefore, the number of electrons is Q over E. He said it is 1 micro. We can ignore that minus sign because we're interested only in the number, okay? Such as this number, 6.24 billion electrons. So we just, the minus sign doesn't mean anything here. Okay, so the fundamental charge is 1.602 times 10 to the -19. And then the charge that is given to us is 1 micro, which is 10 to the -6 coulomb, correct? And that's it. And now, if you insist on putting the minus, that's okay. He said it's a minus. Remember, in the problem, he said it's a minus sign right there. So you can put a minus, and then the charge on the electron would be minus, and then minus and minus cancel out. You end up with positive. You see what I'm saying? So either, it doesn't matter. But the number must be positive, all right? It makes sense that the number of something is always positive. So anyway, so we just calculate that. Again, using my calculator. So 1e -6 divided by 1.602 -19. Answer. If I did it correctly, it will be 6.24 times 10 to the 12 electrons. This is how many electrons in that, whatever it is, that ion or whatever it is. What did he say what it is? Oh, it's a plastic block, so a large plastic block, okay? All right, good. Now, let's go to part B. He says, when rubbed with a silk cloth, a glass rod acquires a net positive charge of 1 nano. I just did this problem, right? If the rod contains 1 mole of molecules, what fraction of the molecules have been stripped off the electron? Stripped off an electron. Assume that at most 1 electron is removed from any molecule. Okay, so basically what he's saying is the following. First of all, he's saying that the charge now is 1 nanocoulomb. He said, what are the number of electrons in that 1 nano? We just did this problem, guys, right? So I'm just going to take out the number that I just got, which is right here, right? For this ion. So in this case, the number here, N sub E, is going to be equal to 6.24 times 10 to the 9 electrons. Now, the next part, he says, move to the next page. He says, what fraction of the molecules have been stripped off the electron? Okay, now he said it's 1 mole. What does that mean? When I say 1 mole of molecules, do you remember, go back to your chemistry class? 1 mole of molecules. That means it's Avogadro's number, remember? 1 mole is Avogadro's number. So this is N sub A, Avogadro's number. What is it? 6.02 times 10 to the 23rd molecules. Okay, so what is the fraction? Well, the fraction is going to be the number of ions, right? Or what I call the number of electrons. This is the number of ions right here, right? To the number of to the Avogadro's number, my number of ions is 6.24 times 10 to the 9 divided by Avogadro's number, and the fraction is 10 to the negative 14, which is very, very small, right? But anyway, that's basically what he's done. He just want to get the ratio of that. Okay, good. Moving on. Looking at the book here. Oh, yes. Okay. Now I'm going to use, I mean, that's all I wanted to talk about as far as the charge is concerned. I want to move on to Coulomb's law, the force law. So just to brush up, we said that the force, the Coulomb's law, says that the force is equal to K, Q1, Q2 over R squared. Please memorize it. And we know that the value of K here is 9 times 10 to the 9. I think your book uses 8.99, which is really close. So these are the two expressions we need to know. I want to do problem number, well, before I do it. So let me just give you a simple example from my head. So let's say I have an electron. Let's say you have the hydrogen atom. If you remember from your chemistry class, the hydrogen atom is the simplest atom, of course, in the periodic table, and it's made out of only, the nucleus is only 1 proton. There are no neutrons. And also, you have 1 electron going around. So it looks something like that. So here is the proton, and then here is the electron going around it like that. Here is the electron right here. It's minus. So that's the electron. It's a negative. And then you have the proton, which is also has a fundamental charge, but it's positive. You see what I'm saying? And then the distance between them, we refer to it, we'll call it R. It's called the Bohr radius. It doesn't matter. But that's called the Bohr radius. So if I am interested in what is the force of attraction between the electron and the proton in the hydrogen atom, okay? Repeat. What is the force of attraction between the electron and the proton in the hydrogen atom? So what is that equal to? Well, in this case, I can use the Coulomb's law. So what I'm looking at here, basically, is the Coulomb's law. So you have F equals to, again, keep your eye on this formula. So it's going to be K, the charge on the electron, which is E, times the charge on the proton, which is E. And by the way, never put minus signs for the charges when it comes to forces, okay? Always just put the positive quantity of it. Divided by the Bohr radius, I think it is 5.29 times 10 to the negative 11 meters squared. Sorry, let me look it up very quickly. I think it's true. Let me look it up on the web. I think it is. Bohr radius. There we go. 5.29 times 10 to the negative 11 meters. That's right. Okay. So, and then all we need to do is to calculate that. Let me just make it look better. So I have here K E squared over 5.29 times 10 to the negative 11 quantity squared. And go ahead, bring your calculator, please, and calculate that with me. So let's see. So I have here 1.602 negative 19 divided by 5.29 negative 11, and I give you this squared times 9. I got an answer of, I hope I did it right, 8.25 times 10 to the negative 8 Newton. There we go. Okay, if it's correct, I hope it is. So this is the force between the electron and the proton in the hydrogen atom. You got it, guys? Okay. Let's do something a little bit more complicated, and that is example number 17.3. I'll show it to you. (17.3). It's the next page. What after? There it is, right here. Should I make it a little bit bigger? Maybe you're not seeing that. Let me make it a little bit bigger. There we go. Is that better? Okay. So let's read it together. He says, now let's apply Coulomb's law and the superposition principle to calculate the force on a point charge due to the presence of the other nearby charges. Okay, so here's where the problem starts. 2 point charges are located on the positive x-axis of a coordinate system. So we have a Cartesian system. Here's y and this x right there. Do you see it? Or maybe those two. Okay. Charge 1 is equal to 3 nanocoulomb at 2 centimeters from the origin, and charge 2 is equal to negative 7 nanocoulomb, and is 4 centimeters from the origin. Then the question is, what is the total force exerted by these two charges on a third charge, Q3, 5 nanocoulomb, located at the origin? There we go. So this is the diagram that I have, okay? Always, whenever you start working on a problem, always draw the free body diagram so you know it will help you a lot in how to solve the problem. I'm not going to follow his solution. I'm just going to follow my own. So let's read it. Let me just draw the diagram for you. So what I have in here is, let me draw the diagram for you. It looks something like that. So here's my Cartesian system. Here's the y-axis. Here's the x-axis. I'm trying to make it as clear as possible. Then I have a 3 charges. Okay, one is located at the 2 centimeter mark. So it is a 2 centimeter mark. So here is a positive charge right here. And that's, I'm going to call it Q1, and it's equal to 3 nanocoulomb. And then this one is on the 4 centimeter mark, I think, isn't it? Sorry. You know what would be a good habit for you if you just open up the book while you're watching all of that. Anyway, so we have, 4 centimeter mark, and it's equal to negative 7 nanocoulomb. So that's a negative charge, and it is negative, I'm going to call it Q2, negative 7 nanocoulomb. And then he says there is one right at the origin, okay, right here. But I'm going to put it here just for clarity. And I'm going to call it Q sub 3. He calls it Q sub 3 anyway. And that's equal to, what is it, 5? It is 5, yes, 5 nanocoulomb at the origin, okay? And the question, let's repeat the question again. He says, what is the total force, okay, the net force, you know, just like the mechanics, what you studied in 151. What is the total force, magnitude, and direction exerted by these two charges on Q3, okay? All right, how do we do it? Well, here is the diagram. Remember, this is the 0 centimeter mark. So we have this diagram. So what you want to do is you want to look at, remember, positive charges or like charges repel, opposite charges attract. So here is Q3 right here. This is Q3. Here is X and Y. Right? So as far as Q1 is concerned, and Q1 with Q3. What would be the direction of the force on Q3 due to Q1? That's going to be a repulsion, right? And that repulsion force is going to go this way. F1. Remember, this F1 is coming from Q1. It's a repulsion, so it's going to push it away. You see what I'm saying? It's not going to attract it here. It's not going to attract it to Q1. It's going to push it away. It's going to repel it. So it's going to go in that direction. You got that? However, the force due to Q2 on Q3, that's an attraction, is going to pull it towards it. You know, opposite attract. So it's going to attract it this way. So there will be another force going this way. I'm going to call it Q2 because it is due to charge Q. It's this way. You see what I'm saying? And now he's asking, what is the net? What's the net force? That's what he's saying. Well, F net in this case, or the summation of the forces, is going to be minus F1 plus F2, correct? Minus F1 because it's going to the left. And I have everything pretty much, really. All I need is just plug it in and you're done. So that's going to be, let me just write down explicitly those expression. That's going to be minus K, Q1, Q3 over the distance between them, which is this distance right here, right? Let me give you a term R1. How about that? Can I call it R1? You know, you call it whatever you like. And I'm going to call this R2 because it's Q2, you see what I'm saying? So this is over R1 squared plus K Q2 Q3 over R2 squared. You see what I'm saying? And now all we need to do now, I mean, we can make it look better by doing some algebra just to simplify things. What's common between them is K and Q3. I can just take them as a common factor, so I can, I would reduce my calculations. So I have minus Q1 over R1 squared plus Q2 over R2 squared, and that's it. Just plug in. So I have 9 times 10 to the 9. This is for value of K. Q3 is given to me 5 nano, which is 5 times 10 to the 9. And bracket minus. Remember, this minus came from where? Where does this minus come from? This minus comes from the direction of the force guide to the left. Okay? Keep that in mind. Okay, so I have minus Q1 is, oops, forgot what it is. Q1 is 3 and Q2 is 7. So Q1 is going to be 3 nano, so 3 times 10 to the negative 9. Divided by the distance between them is 2 centimeters, so 2 times 10 to the negative 2 quantity squared, correct? Plus, I'm right here, plus Q2, what is Q2 is equal to? What's that number? Don't say negative 7, it's positive 7. Yes, it is negative 7, but when you come to putting it into the formula, you always put it positive. This is very important. Never put a negative sign on a vector quantity. The force is a vector quantity. Don't put it there. So anyway, so we have here 7 nano, so 7 times 10 to the negative 9. Don't put the negative. Divided by, how far is it from Q3? Well, it's 4 centimeters. That's going to be 4 times 10 to the negative 2 quantity squared. That was a lot of calculations to do. So anyway, go ahead and calculate that, and I have done that already. And if you, well, let me give you one more step here. I have it in my notes here. When you calculate this by itself, I'm going to give you 45 with the 9. See, this 9 and this one will cancel out, and this will count. There is a little trick to it. If you work it out, you'll end up with this. Negative 7.5, I'm copying this from my notes, times 10 to the negative 6, plus 4.38 times 10 to the negative 6. And then you calculate this, and you'll end up with negative 1.4 times 10 to the negative 4 Newton. Okay? So that's the net force. Okay? What does that mean? What's the meaning of that? Well, it means the net force between them in the negative x direction. What that means, if I go back to this one here, the net force is going to be something like that. That's net. In the negative x direction, pointing in the negative x direction. That's the net force. You got it? And there we go. Okay. One more problem. This one a little bit harder, 17.4. It requires some trigonometry. And then I'll move on to the topic of electric field. Example, in the book, 17.4, I'll show it to you. Kind of a two-dimensional problem. Let me show it to you in the book. I think it's next page. There it is right here. There's a diagram to it right there. I think this one, or I'm not sure. Let's read it together. He said, in this example is similar to the preceding one, but now we will consider a two-dimensional arrangement of charges. A point charge Q1, right here. See it? Here's the picture right here. Here's a charge Q1, 2 microcoulomb, is located on the positive y-axis at 0.3 meters. Okay, and an identical charge Q2 is at the origin right there. Okay, so we have Q1 and Q2. They're both on the y-axis. Q1 is at 0.3 meters, and Q2 is at the origin. Find the magnitude and direction of the total force that these two charges exert on a third charge Q3 right here. Okay, sitting on the x-axis, that is on the positive x-axis at x equal 0.4. You want to find the net force. Okay, so I'm going to do it my way. Again, you can read his solution. I'm just going to do it my way. But basically, the important thing is this diagram right there, and then you want to do the free body diagram just like this one. And personally, I cannot do this problem without drawing the free body diagram. It's very, very important for me. So anyway, let me show you how to do it. So I'll try to keep it away, within the frame of the video. It's right here. Okay, so it looks something like that. I have x and y. Here's the Cartesian axis. This is y, and this is x right there. I'm still getting used to this, the new stylus pen that I have, so excuse my crooked lines. And I have one positive charge right here, and another one here, and then I have another one. They're all positive, correct? Yes. Okay. And a one right there. This is 0.4. I'm not going to write the unit, but it's understood. It says 0.4 meters. This is 0.3. And this one is Q1, 2 microcoulomb. And this is Q2, also 2 microcoulomb. And Q3 is equal to, what is it? 4? I think it's 4. Sorry. 4. Right there. Okay. And he wants the net charge, the net force on Q3 right here. Okay? So how do I do that? Well, let's see. As you can see, all these charges are positive. So that means all of them are repelling one another. Like charges repel one another. But I'm only concerned on Q3. What are the forces on Q3? Well, I have two forces here. One due to Q1, and the other one due to Q2, correct? So in this case, I'm going to have something like this. Let me change the color of the pen. How about that? I'll make it red. So in this case, I'm going to have a force that looks something like that. This is, I'm going to call it F1 because it's due to Q1. And then I have another one, I'm going to call it F2, horizontal, due to Q2, right here. And of course, there is an angle between them. Remember this resolution of vectors from chapter 1 or 2 from one of your 151 class? So we have to resolve vectors into x and y components here. F2 is fine, there is nothing wrong with it, it's along the x-axis. But F1 is the troublemaker, we have to get two components, one x and one y, you see what I'm saying? The issue here, however, is that I need to find the angle, which is this one. This angle right here, the angle theta, sorry. But if I find this angle, then I'm done. Okay? So what I have in here, let me change it to the black color. So what I'm looking at a triangle that looks something like that. And this is 0.4, and this is 0.3. You can imagine that this one is 0.5. You agree with me? You know, it's a 3, 4, 5 triangle. And I want to find this angle theta right here. I can use sine, cosine, or tangent. I'll use tangent. So tan, this angle, is equal to opposite over adjacent. And it's basically theta is equal to, let me use my calculator very quickly. And that's equal to inverse tan 0.75, right? And the answer would be 36.87. So that would be 36.9 roughly. There we go. That's the angle, which is the same as this angle here. This angle right here, right? They're both opposite angles. Okay, so I have that. So all I need to do now is to resolve the vectors. I need to resolve this vector F1 into two components. One component, let me put a different color for that as well. Maybe green. You like green? So in this case, I'm going to have a vector, bring it down a little bit. I'm going to have a vector F, sorry, this is horizontal. I'm not doing a good job here. F1x. And then there's another one here, F1y. You see what I'm saying? So let me work on F1x. So F1x is equal to F1 cosine theta, and F1y is minus F1 sine theta. Is that right, guys? And of course I can, you know, theta, I already know what theta is, so I don't need to bother with it. So there we go. Now, he said he wants to know the net force on Q3. So I need to find the sum of the forces. Let me go back to black color. So I need to find the net, the x component first of all of that. So the sum of the forces in the x direction, well, what do I have? How many forces do I have in the x direction? Oops, sorry. I have to do it with my hand. Actually hold my hand on the screen and scroll it down. The mouse doesn't do a good job. So anyway, so I have two forces here. I have F1x and F2. They're both on the x-axis. All right, guys? So that's going to be plus F2 plus F1x. More details in a minute. And then some of the forces in the y direction, there's actually only one force right here. That's just going to be negative F1y, which is negative F1 sine theta is right there. This one, which is here, right? Those two. Okay? And so I'm building it up slowly. Now I need to work on both of them, starting with sigma f sub x. That's going to be F2 right here. Well, what is F2? Just Coulomb's law. F2 is this Q2 and with Q3, the distance between them is 0.4. So just K Q2 Q3 over R squared, which is 0.4 squared. So that's going to be K Q2 Q3 over 0.4 squared. Is that right? Okay. So remember, I am working on this one right here. That's the first part for this one. Now the second part. Plus F1x. I already told you what F1x is, right? Where is it? Oh, right here. right there. So that's going to be F1, which is basically what? F1 is K Q1, Q3 over the distance between them, which is the hypotenuse. Is that right? So that's going to be K. F1, which is Q1, Q3 over the distance between them, is 0.5 squared. Is that right, guys? This is Q1, this is Q3. The distance between them is the line connecting them, which happens to be the hypotenuse of this triangle, which is 0.5. Okay? Times cosine theta. So times cosine, what is it? 36.9. And there we go. Just plug in your numbers and work it out with your calculator. Just, so you're going to go 9 times 10 to the 9. Q2 is equal to, it's in the micro? No, micro. So that's going to be Q2 is equal to, okay, Q2 is both 2. Okay, that's going to be 2 times 10 to the negative 6 times 4 times 10 to the negative 6 divided by 0.4 quantity squared plus 9 times 10 to the 9. As you can see, there's a lot of number crunching. 2 times 10 to the negative 6 times 4 times 10 to the negative 6 divided by the distance between them, 0.5 quantity squared, times cosine 36.9. Then you work it out, and I have it in my notes. I hope I do. I'm going to believe that I've done it correctly. Let's just assume that. So when you work it out, I got 0.68 Newton. That's it. Nice number. I'm going to do the same thing for F sub y, which is right here, this one. Okay? So I'm going to do the same thing. So therefore, sigma F sub y, and I think you can do it, but let me tell you, so minus F1 sine theta, that's just going to be minus K Q1 Q3 over the distance between Q1 and Q3 is 0.5, right? Quantity squared sine 36.9, and we work it out. And when you work it out, I ended up with, remember there's a minus sign here, that makes it a little bit different. I'll end up with negative 0.173 Newton. Okay? There we go. So basically what I have done here, I have gotten the components of the two vectors. Now, what is the vector? Well, the vector is the Pythagorean. This vector f is basically the square root of f sub x squared plus f sub y squared. You see what I'm saying? This is f sub y right here, and that's f sub x right here. All you need to just plug him in there to find the value. So that's going to be square root of 0.68 squared plus negative points, rather. My erase is not working. There we go. 0.173 squared. Work it out, you end up with F equals to 0.7 Newton. There we go. I have the magnitude of the force. Okay? And then, or the F net, if you will. Okay? And then the angle. What's the angle? Well, the angle, I mean, there's a law to it, just memorize it. The angle between them is always tan inverse of f sub y over f sub x. I have f sub y, which is right there, and I have f sub x, which is right here, right? Just plug it, get the ratio and then the tan inverse to me. So that tan inverse of negative, negative 0.173 over 0.68, and then when you work it out, you'll end up with negative 14.3 degrees. Okay, what's the minus mean? It means below the x-axis. In other words, this net force, go back to the diagram, which makes sense. Look at the theta right here, guys. It's below the x-axis, so we should expect it to be negative. and we got 14.3 degrees. Let me see what he got. I don't know if he did it correct. I mean, not correctly, similar to mine or not. But he got negative 14 degrees. That's good, close enough, and so on. Okay, and he got the total, or the net is 0.7. I got 0.7, same thing. Okay, you got that, guys? Okay, good. And that's basically what I wanted to talk about as far as forces, Coulomb's law is concerned. Let me move on to the last topic of this chapter, and that is electric field. I'm looking at my hard copy here of the book. It's easier to flip pages. And it's on page 540. That's where the electric field is. Let me just go there. 540. 540. Right there. This one right here. So the electric field due to a point charge is equal to that. Okay, let me talk about it. Think of the electric field just like the gravitational field. What is the gravitational field of the Earth? I mean, here is the Earth, right? And anything you are holding in your hand and then you release it off your hand is going to fall to the ground, correct? Well, why does it fall to the ground? Well, we say it falls to the ground because of gravity. Well, can you be more specific? What is a better answer is that there is a gravitational field due to the Earth, to the mass of the Earth. And that gravitational field is always pointing downward toward the center of the Earth. So think of it like this. Here is the Earth right here. Here's the center of the Earth. Think of it like there is a field or field lines. Let me draw them. And those field lines are always pointing toward the center, like this. Here's the center. So any object that happens to be in the vicinity of that field is going to follow the line of the field lines. And it's just going to fall to the ground. You see what I'm saying? So with this we call it the G field. Okay? So similarly, we have an electric field. Same thing, exactly. And this electric field, well, since we have two charges, positive and negative, those two fields come kind of two flavors to them as well. If you have a positive charge, this field will, the same thing, it is pointing in the radial direction like that, just like the gravitational field, but it is outward. Keep that in mind. This is very important. Plus is outward, not downward. Okay, that's the electric field E. I'll put a vector on it like that. Okay, that's if it's positive, it's outward. If it's negative, however, it's downward or inward. So it's exactly the same, identical to the positive field. The only difference is the direction. So this one is inward. One way to remember it is like when you say positive, like plus, surplus, like you have things and you can overflow, you can give away, so it's plus. Where if you have a minus sign, it means like you are in the minus, you need, so you intake, you see what I'm saying? That will be one way to remember it if you want to. But anyway, there they are. So they both have the electric field. Now, if I have this charge, let's go back to the positive or negative, whatever, and it has a charge Q, okay? So this electric field is equal to KQ over R squared, sorry. What does that mean? It means the following. Let's say, for example, here's a charge. Let me draw my Cartesian system. I could never draw a horizontal line with this stylus pen. There we go. Okay. And let's say I have a positive charge right at the center, at the origin right there. Okay. I would like to know the intensity of the electric field at this point. At the distance r equals, say, 1 meter. Okay, I want to know E here. How do I do that? Well, first of all, what is the direction of the electric field at this point? Remember we said the electric field, if it's positive, it's outward. There it is right there. If it's negative, it's inward. That's the first thing. Second thing is that if it's positive or negative, the direction of the electric field is always in the radial direction. What that means is that the direction of the electric field at this point right here is really this way, radially. Away from it radially. It's not away from it this way. That's away from it as well, but it's not radial, or this way. That's away from it too, but it's not radial. It got to be radial. You see what I'm saying? So it's away from it radially. So if I say, what is the electric field intensity at this point right here at R equals 1 meter? Well, it's just KQ over R squared. Let's assume the Q here. Pick a number, what you want. Let's say 1 microcoulomb, okay, for example. So what is the electric field intensity there? Well, this electric field, I'm following you from here, that's going to be 9 times 10 to the 9 for K. Q in this case is 1 times 10 to the negative 6, so that's going to be 1 times 10 to the negative 6 Coulomb, divided by, how far is it? 1 meter squared. And then I can just calculate that. That's going to be what? 9 times 10 to the third. It's basically 9,000, right? 9,000 watt. Well, 9,000 electric field. There is another relationship that, well, I'll come back to it. But anyway, the unit of electric field for now is Newton per Coulomb. Okay, memorize it, please. Newton per, later on, there will be another unit. It's volt per meter. We'll come back to that later. But for now, the unit of the electric field is Newton per Coulomb. And there we go. We have calculated the intensity of the electric field at 1 meter away due to this charge, which is just 1 microcoulomb. You got that? Okay. Another relationship that is of importance is that, remember we said that the Coulomb's law is equal to F equals K Q1 Q2 over R squared, and we said that the electric field is KQ, let's make that Q1, okay, or 2, whatever, over R squared. Look at that, I can actually insert this thing in here. See, if I take this part right there, that's equal to the electric field, you see what I'm saying? So therefore the force is equal to QE. I'm going to drop the 2, forget about the 2 for now, this 2 here. So it becomes QE. See that? So that's another relationship for Coulomb's law. F equals QE. Or E is equal to the force over the Coulomb. Okay? So these are another expression, or this, when you're asked, well, how is the electric field E is related to, or this E is related to the Coulomb law, the relationship between them is this one. Okay, this is how relation between E and F. Okay? I mean, I can go on about it, why is that so, but for now, just accept it as is, okay? I mean, if I'm teaching a course on electricity and magnetism, an advanced course, there is a reason why those are related, but it's not important for our case here, for this course. Just accept it, okay? All right, good. Let me look for an example and show you how that works. Oh, yes, that's a good one. Example 17.5. I would like to do maybe a couple of examples before I move on to the problem from the homework. Maybe 17.5 doesn't look bad. Let me go to the book. What is 17.5? Here's my. It's on page. Oh, page 539. Is it? I'm sorry, that's not what I wanted to do. That's not the electric field. I apologize. I think I wanted to do 17.5. I paused the video for a second just to see what's going on, but yes, that's the one I want to do. Maybe I'll do another one before we do the problem. So let me work on example 17.5. Okay, it says, let's read it together. It says, and as you read it, please look at the picture right here. Think of it like this is think of it like a negative plate right here, and this is a positive plate, and as a result of that, you're going to have a uniform electric field. Remember, electric field goes from positive to negative because positive is outward and negative is inward. So you're going to have an electric field in that direction going up, instead of saying from positive to negative. And those plates are separated by a distance 1 centimeter. I'm telling you all of this before I read the problem. And then there is a negative charge here, and he's asking some question. Okay, let's see. In this example, we will analyze the motion of an electron. Okay, here's an electron right here. That is released in an electric field. So the electron is sitting or is being forced to be in the negative. Remember, it's being repelled to be in the negative because the electron itself is negative. The terminals of 100 volt, okay, that's a battery, are connected to the two large parallel horizontal plates of 1 centimeter apart. Okay. The resulting charges on the plate produce an electric field E, and that's E is equal to, there it is, E equal to 10,000 Newton per Coulomb, 10 to the 4 Newton per Coulomb. Suppose the lower plate has positive charge so that the electric field is vertically upward. Okay? If an electron is released from rest, so I'm holding the electron here. See this electron? Imagine I'm holding it between my fingers, okay? And then I'll let go. What's going to happen to it? It's going to shoot to the positive, right? It's going to be attracted to it, instead of saying. So it's released, so I'm holding it, so it's released from rest. So if the electron is released from rest in the upper plate, what's the speed just before it reaches the lower plate? Okay. How much time is required for it to reach the lower plate? And they give you the mass of the electron, 9.11 times 10 to the negative 31 kilogram. Okay? It's kind of an interesting problem. Before I do it, let me go back to kinematics. So something that you studied back in 151. Before I do that, kind of just to give you a brush up of what's if you remember free fall. Remember free fall? So let's say you have a height like that. Okay? And let's say this height is h equals 10 meters. Okay? And let's say I'm standing and I'm holding an object right there. Okay? I'm holding it between my fingers. And then I'll let go. Okay? So what's going to happen? It's going to fall to the ground. Right? Okay. I'm asking the following question. What is the speed of the object, this object right here at the bottom, just before it hit the ground? Remember, at the top here, released from rest, that means the initial velocity is 0. I want to know what is the velocity here just before it hit the ground. I mean, after it hit the ground, it stopped, 0. But right before it hit the ground, what is the velocity, given that the height is equal to 10 meters? Okay, that's basic free fall kinematics. How do we do this problem? Well, we can use the energy method, which we're not going to do that now here, or we can use kinematics. If you remember kinematics, one kinematic problem would be, one kinematic equation rather, is, remember the kinematic equation? Here they are. Let me just write it down for you. It is V equals V naught plus A Y, V squared, I'm sorry. It's AT, right? V squared equals V naught squared plus 2AY. And then Y equals V naught T plus 1/2 AT squared, correct? These are the equations of kinematics. I can pick any of them. Since time is not given to me here, I'm going to pick the middle one. The middle one doesn't contain T. See, this one contains T right there. This one contains T. So I'm going to pick the middle one. So it says V squared equals V naught squared plus 2AY. And because we are dealing with free fall, so A here is equal to G. And G, because it's downwards, so it's going to be negative, if you remember those details. So it's going to be negative GH. H is the height, this height. So that's the free fall kinematic for this situation. So now, if I want to know the velocity just before it hit the ground, well, starting with 0, v equals 0 here, right here, v is equal to 0, so that's 0. So the velocity v squared is equal to minus 2 times 9.8 times negative 10, right? Because this is, you're measuring height from here, anything below it is negative, and that's, so in this case, v squared is equal to 19.6 times, that's going to be 196, I think, positive, and therefore the velocity will be the square root of that. So when I do that, square root of 196, answer 14 meters per second. And there we go. This will calculate for me the speed of the stone or the object just before it hit the ground. You got it? I'm going to do something. I have something very similar to that. What do I have? I have the following. I have, before I do this problem again, I have a negative plate. Here is a negative plate. Okay, and I have a positive plate here. Oops. If I can draw a straight line. I have an electron right here. And I'm holding it between my fingers, and I'll let go. What's going to happen to it? It's going to fall toward the positive plate. Just like the stone here is falling toward the ground. Just like exactly the same situation. You see what I'm saying? The only difference is that here we have a gravitational field toward the Earth going this way. That's the gravitational field G, if you will. Okay? Well, we have the same thing, except that it is electric field. And that electric field is in the positive direction, from positive to negative, that is. But it's really the same thing, okay? So now he's asking, what is the speed of the electron just before it hit the positive plate? See the similarity between them? So, well, okay. So I can basically use the same kinematic equation, this one. Same kinematic equation. I mean, it applies to anything. The only difference is that this A is not, this A right here, is not G. You see what I'm saying? It's not G. G is for gravity, acceleration due to gravity. It's got to be something, it's not a free fall. The electron here is not falling free fall. But we got to use it, but in such a way that this A is something else. I don't know what it is for now. But it's not definitely is not G. I hope you believe that. So all I know is that I know I'm going to use this equation somehow. So I'm going to write it down. Now I am solving this example, okay? So it's going to be v squared, v naught squared, plus 2ay, where y is the distance. I don't want to call it. You can call it h if you want to. I'm going to call it y, okay? And of course, it's starting from, he said it started from rest, so that's 0. So that's 0 right here. So I have v squared equals 2ay. Now, he gives me y. See that? If you look at the diagram in the book, he gives you y right here, 1 centimeter. So that's no problem. He gives me y. So I don't have a problem with the y. The troublemaker is a. What is a? A is acceleration. Well, what is that equal to? You see what I'm saying? Now, he also gives me E. He said it's, forgot what it is, 10,000 or something. Okay? So here is how you work it out. Look, we said that the force is equal to QE. Remember? Above? Right there. Also, we know that the force F is equal to ma. Remember? Newton's second law applies to everything, really. Now you see where I'm going with it. Now I can find A from those two expressions. See, I can equate those two together because they are equivalent. So I can say QE equals ma. Therefore, A is equal to QE over M. There we go. You see what I'm going with that? Now he says in this problem that it is an electron. Did he say it's electron? Yes. I'm reading it from the book. Let me go back. I should read it together. Is that an electron? I think it is. I'm sorry. There we go. Electron. Finally, I found it. Yes, it's an electron right here. Okay? So it is an electron. So what does that mean? Well, I know, oh, and he also gives me the mass of the electron. And what is Q on the electron? This Q right there. What's Q on the electron? It's E, the fundamental charge. Remember, beginning of the lecture I told you that? The electron and the proton are basically E, simple. So in this case, the acceleration really is EE over the mass of the electron. I got everything. So I can find the acceleration without any problem. The fundamental charge, 1.602 times 10 to the negative 19. The electric field, he gives it to me, I believe 10,000. Right there, 10,000. 10 to the fourth. Divided by the mass of the electron, 9.11 times 10 to the negative 31 kilogram. And there we go. I can use this data to calculate the acceleration of the electron. So let's do that. Please work with me. So that's going to be 1.602 negative 19 times divided by 9.11 negative 31. Answer, I got 1.76 times 10 to the 15 meter per second squared. Okay, it's not a surprising. It's a very large number, but that's not surprising. Those subatomic particles have extremely large acceleration. And there we go. You got that? So now I can go back to my kinematic equation right here. Okay, and plug it in, and I can find V. So now we have V squared is equal to 2AY. So V is equal to square root of 2AY. And you know the rest of the story, correct? So you just need to calculate that. So that's square root of 2 times A. It is above right there. Times Y, which is 1 centimeter, which is 10 to the negative 2. And then you calculate all of that. And if we calculate it, you'll end up with times 1 negative 2 times 2 under the root. Answer, if I did it correctly, it's 5.9. 5.9 times 10 to the power of 6 meters per second. And there we go. So the electron, by the time it hits the positive plate, is going to be going on a speed of about 6 million meters per second. Okay? You got it, guys? Okay. That's basically what I wanted to talk about as far as electric field is concerned. So let me move on to the problems. If I go to mastering, let me just take that away and then go to mastering physics. Here's your homework. Oh, session expired. Let me go log in again. It's been on since I started the lecture, I guess. So I click on there. And there are the problem, the homework. We are in chapter 17. Oh, by the way, before I forget, the category under mastering is called practice quiz, but it's not a practice quiz, just homework. Okay, I couldn't find the title homework under mastering, so I'm using it practice quiz. But don't be panicked with it; it's just a category name. but it is homework. You got that? Anyway, so we click on that, and then these are the problems that you need to do. A lot of them are pretty easy. The one that I found a little bit challenging is number 38 and 42. So I'm going to go over them with you. Let's do them both, and then I think the rest should be relatively easy. I mean, let me know. Just post them under Ask the Professor. I'll be more than happy to help you if you have any issues with them. But anyway, okay. So let's do number 38. Well, let me just go to the book. I think it's better if I just use the book, because the one on the mastering, they have different data. You see what I'm saying? Than the book, same identical problem, but it's just different data. So anyway, and if you remember how to get to the problem from the book, you just go. We are in chapter 17. So what you do, there's a little trick to it. The one I showed you, you go to chapter 18 and you go backwards. Then you go backwards to problem number 38. Sorry, when I got there. There we go. There it is right here. Okay, let's read it together. It says the proton is traveling horizontally to the right at 4.5 times 10 to the 6 meter per second. So we have a proton traveling at 4.5 million meters per second. He said, find the magnitude and direction of the weakest electric field that can bring the proton uniformly to rest over a distance of 3.2 centimeter. Okay, sounds like a tough problem, doesn't it? Okay, so how do we do this one? Well, first of all, you want to draw the diagram, then I'll tell you how to solve it. So I have a proton, there it is, and I'm shooting the proton with, with initial velocity v0 given to me. It is 4.5 times 10 to the 6. Oh, I reached the top. I can't go any further. 6 meters per second. And then here I have, remember this is a proton, so that means I'm going to have a positive plate here. Why do I have a positive plate here if I shoot it against? Well, when I have a positive plate, that means the proton is going to be repelled by this positive plate, correct? So if I shoot it against it, what's going to happen to it? It's going to go, and at some point, it's going to stop somewhere, and it's going to rebound. Make sense? Another way of thinking about it, let me draw it in a better way. Let me just draw the whole thing again. This is not wrong. I just want to draw it in a better way so you can understand it. Imagine I have a positive and negative plate, okay? Here's a negative plate. Here is a positive plate. This is positive. And this is negative. And let's assume here, so in this case, there is an electric field going this way, right? Which direction is this electric field, guys? It's going to be this way, correct? Got positive to negative. Let's assume that I bring in a proton, here it is, and I shoot it with velocity v0. What's going to happen to it? It's going to go like this, and it's going to reach a certain point. We call it in nuclear physics the DCA, distance of closest approach, and then it's going to rebound. That's the DCA right here. That's called a DCA. Okay, so you shoot the electron with velocity 4.5 times 10 to the 6 meter per second. What else? What other data he gives me? Sorry. Find the magnitude and direction of the weakest electric field that can bring the proton uniformly to rest over a distance of 3.2. Okay, so what he's saying, what is the intensity of this electric field? Right here, this one, this electric field. What's the intensity if the electron can go only for a distance of 3.2 centimeter before it returns, before it reaches the DCA? You see what I'm saying? Everybody understand the problem? I'm not telling you about the solution. I'm not asking you how to solve the problem. Always make sure you understand what the problem is asking for first. Then you start sort of looking at the solution. Okay. How do we do it? Well, again, we can use energy method. We're going to do that later in the chapter, later in the semester. But for now, we are big on using kinematics. Okay? So here I have the moment I shoot the electron in this stage right here, the electron will start decelerating. Okay? And it's going to decelerate to a final velocity here of what? Of 0. It's going to stop, right? Over a distance x right here. So here we have x is equal to 3.2 centimeter. You want to convert it to meters, of course. And then the final velocity is 0. As you can see, this one is basically a kinematic formula, kinematic variable, so it requires a kinematic formula. Which one? Well, we can use the second one, the one I just used for you. We can use this one. V squared equals V naught squared plus 2ax. Why do I use this? Because the time is not given to me, but x is given to me. The final velocity here is 0. See what I'm saying? And acceleration here is negative, right? Because it's deceleration. So let me find the acceleration. Why do I find the acceleration? I'll show you in a minute why. Let's find the acceleration. Solve for it. So that's minus V naught squared over 2x. Plug it in. Don't impose the minus. The minus will come out automatically. It's going to be minus. The V naught is equal to 4.5 times 10 to the 6 quantity squared, right? It's right here. Divided by 2x. So that's 2 times x. X is what? 3.2 centimeters. So that will be 3.2 times 10 to the negative 2 meters, right? You have to put it in meters. And then you would calculate. You would calculate the acceleration. Is that right? Okay. I'm going to leave that in a minute. I'll do the calculation, but I want to go a little bit further. Let's say I got a number here, which is a simple number. Well, let's just calculate. Sorry about that. Let's just calculate that. So I'm going to calculate this, and that's going to be 4.5 E6 squared divided by 2 divided by 3.2 negative 2. Answer. My answer is negative 3.16. If I did it correctly, I hope I did, times 10 to the power of 14 meter per second squared. That's the acceleration rate of the electron. Electron, or what is it? Proton, electron? Okay, proton. He says he wants what? He wants, what is the weakest electric field? What's the electric field? This one. Remember I told you about the relationship between acceleration and the electric field. F equals ma, and F equals QE. Therefore, QE equals ma. Since it's a proton, so it has a fundamental charge, ma. So therefore, E is equal to ma over E. Isn't that nice? That's it. It's easy. That's all you need to do. So all you need to plug it in. I have the electric field right there. The acceleration right here. And I get the mass of the proton. So I go 1.67 times 10 to the negative 27. That's the mass of the proton. You can look it up if you want, but that's it. I just happen to memorize it. Times 3.16 times 10 to the 40. I'm going to ignore the minus sign for now because I want to get the magnitude of it. Divided by the fundamental charge, which is 1.602 times 10 to the negative 19. And then we just calculate that. And when you calculate it, I got, let me keep the minus sign here. I don't want to confuse it. It's probably somebody saying, why do you ignore it? Okay, let's just keep it. So that's, in this case, I'm going to have, if I calculate that, I'm going to use my calculator. So I do that. 1.67 negative 27 divided by 1.602 negative 19. Answer, negative 3.3 times 10 to the 6 Newton per Coulomb. And there we go. Got it? The second part of the problem, I think I'm going to leave it to you as an exercise, simple. Second part of the problem, he said, how much time does it take the proton to stop after entering the field? Okay, basically, if you go back to the picture, what he's saying, how long it will take the proton to go from here to here. Okay, again, that's just kinematic. He's asking for time. So that will be the first kinematic equation, V equals V naught plus AT. Of course, that's final, so the time would be V minus V naught over A. If A, of course, is the minus, and you just plug it in. It shouldn't be difficult, right? And part C, he said, what the minimum field, he's asking the same question, would be needed to stop an electron under this condition. So basically, you want to do the same problem, redo it, but this time you're not using a proton, you're using an electron. The only difference, I believe, is just the mass. So here, using the mass of the proton, which is this number, 1.67, negative 27. The mass of the electron is 9.11 times 10 to the negative 31 kilogram. So you're just going to take the same formula, plug it in with this number, and that will give you the electric field for the electron. You see what I'm saying? And that's it. Okay, good. I hope this problem is understandable for you. The next one I want to do is number 42, I think. Is it 42? That's what I said? 42, yes. And here it is right here. He says, let's read it together. Okay, it says two particles having charges positive 0.5 nanocoulomb and positive 8 nanocoulomb are separated by a distance of 1.2 meters. A. At what point along the line connecting the two charges is the net electric field due to the two charges equal 0? Okay? The second part says, where would the net electric field be 0 if one of the charges were negative? Okay. All right, let's move it to the side. Okay, so what we have in here, let me read it and then draw the diagram. Two charges of, two particles of those charges are separated by distance 1.2 at a point along the line. Okay, so let me draw that. So I have here two charges. This is part A. One positive. They're both positive, right? Okay. And here's another one right there. That's positive as well. And they're separated by a distance of 1.2 meters. This is Q of, 0.5 and 8. Okay, so I'm going to call that 0.5 and 8. So this is 0.5 nanocoulomb, and this is 8 nanocoulomb. As you can see, the difference between them is really large. I'll call that Q1 and Q2. How about that? Okay, he says at what point along the line connecting the two charges is the net electric field due to the two charges is 0? What does that mean? Well, look, let me pick any point in space. Let's say here. Doesn't matter where. Let's pick it right here. Okay? That's just a point in space. There's no charge. There's nothing in there. Just a point in space. Of course, the two charges have electric field. Remember I told you if you have a positive charge, you get electric field coming out of it, right? Like that, and so on. So here you have, due to this charge, there will be an electric field going this way. I'm going to call it E1 because it's Q1. And then due to this charge right here, there will be an electric field going this way, and that's going to be E2. Now, if I take this point in space and I shift it right and left, where would I put it in such a way that E1 and E2, excuse me, that's E2, where E1 and E2 will cancel each other out? In other words, the net will be zero. That's what he's saying. Look at that. He said, at what point along the line connecting the two charges is the net electric field due to the two is zero, which means some point here, at some point, some distance here, E1 and E2 will be exactly equal and opposite. They will cancel each other out. They'll be zero. Okay? So I don't know where. So I'm just going to say, let's assume it is this one right here at this point, and it is a distance x away from Q1. You see my assumption? So if this is a distance x, I need to find that x. Now this one here, it would be what? 1.2 minus x. See what I'm saying? So now, E1 would equal to E2. This is where they will cancel each other when the two are equal. Okay? So now I just work it out. So I have here K Q1 over how far is E1 from Q1. Q1 is right here. So this distance is x squared equals to K Q2 over 1.2 minus x quantity squared. As you can see here, the k's will cancel out, and all it basically boils down to an algebraic formula. You see what I'm saying? Quadratic equation. So you can work it out. So if you cross multiply, it's going to be Q1 1.2 minus x quantity squared equals to Q2 x squared, and then you just work it out. It's simple algebra, correct? I hope it is. And then you will find the value of x. You'll end up with a quadratic equation. You want to solve the quadratic equation, and then you work it out. Okay? Part B of the problem, he says, where would the net electric field be zero if one of the charges were negative? Okay, so I'm going to draw it again like that. So let's say let's assume this is the Cartesian axis, x-axis, for example. And let's say this is positive and this is negative, where the negative is Q2. So it's going to be negative, what is it equal to? 8.8 nanocoulomb. So it's going to be negative 8 nanocoulomb. And this one is Q1 is equal to 0.5 nanocoulomb. You see what I'm saying? And where would it be where, I'm sorry, it is again. He said, where would the net electric field be zero if one of the charges were negative? The net. Well, if I pick a point in the middle like I did in the previous problem right here, what's going to happen? Let's see. Due to Q1, the direction of the charge is going to be this way. The direction of the electric field is going to be this way. Due to Q2, the direction of the charge is also inward. It's going to also be this way. So as you can see here, you're not going to get a net between them. Make sense? I mean, they have to be opposite. So this is not going to work here. But if I would put it here, let me just take this arrow. Let's say I put the point right here. Due to Q1, so that's the electric field is going to be this way. That's E1. But due to Q2 is going to be this way. E2. And I think this just one is enough for, you can probably apply the same thing here. So we're going to use this one here. Okay. So now when I do that, so they can be equal and opposite here. So that means E1 is equal to E2. And remember that the distance between them is 1.2 meters. And this distance that I'm looking for, I'm going to call it x. So in this case, it's going to be k q1 over x squared equals to k q2 over, what is it? That will be that point from here all the way here, and that's going to be x plus 1.2 quantity squared. Of course, the k's will cancel out. I have q1 and q2, work them out, and then you solve for the value of x. Again, you end up with a quadratic formula similar to the one here, and you should be able to work it out. Okay? I think I'm going to stop here. Please let me know if you have any other questions, and I'll be checking my the forum Ask the Professor on a daily basis. So if you have any issue with any homework problem, just let me know. Hey, Dr. Raja, I have a question number so and so. I'll be more than happy to help you with it. Okay? And that's it for now. Have a good day. Bye.